Welcome everybody to lecture 1. Today's topics will be vectors, coordinate systems and index notation. The way we will be working with these online lectures is that I will have a presentation going on the left side of the screen, and I will be using the right side of the screen as a kind of a whiteboard on which to illustrate with examples or draw figures, etc. Okay, so let's move on. Okay, vectors. So what is a vector? Well, we all know what vectors are. They are basically objects which are like that. They have a length which we often denote with this. The vector has a notation like that, and it has a direction. Okay. Now, when writing, it's usually easy to use a notation like that, but while typing, usually this is better. Okay, the hat notation is for unit vectors, which will be carried over when writing as this. So that's a unit, that's a vector with length 1. Okay, so here are some simple operations with vectors which we are all familiar with. Let's try. So a dot product. So suppose I have two vectors A and a vector B. Okay, and I can always measure an angle between them, which let's call it theta. Then the dot product is simply as written over there, A dot B is AB cos theta, where, as I have already said, this means the magnitude of the vector, the length of the vector. Well, how do you actually compute the length of the vector? Well, that is easy. We simply use the dot product formula and have theta equal to theta equal to 0 degrees, and we get this formula right here. Okay, the cross product, another operation that we are familiar with, which is defined as A cross B is minus of B cross A, and that is AB sine theta in the direction of E. Now what is that? Let's draw a picture. So let's again use this picture over here. So the vectors A and B will define a plane, and so that's the plane in which A and B lie, and a normal to that plane is this vector E, given by the unit vector E, and A cross B is AB sine theta is the magnitude and E is the direction it's out of the plane. So a cross product, even though it is limited to vectors, can be limited to vectors within a plane, the output is actually out of the plane. Okay, so as you will see, that may lead to something more interesting later on. There's often a thumb rule which is used to compute cross products as to, well, there are two normals to the plane. Why? How do we compute this normal? Why not the other normal? Why not that normal? Okay, so that's because we use a so-called a thumb rule, which is given by this, that if this is A and that is B, then this is A cross B. Okay, and in the current violent times, you may want to use the handgun rule, which well, you can read it on your own later on. Okay, so what's the important message here? The important message here is that we could play around with these vectors. All of these operations we could do, and we did not once have to draw a coordinate system. So we do not require a coordinate system to define and operate with vectors. That is a very important message. Okay, moving on. So coming now to a coordinate system. So after saying that we actually don't need a coordinate system, I'm going to talk about a coordinate system, and that is because even while I can define vectors and operate with them without a coordinate system, if I want to, for example, code them into a program or tell them to a friend who lives somewhere else, and I can't send a photograph of my vector, then I must be able to send them numbers related to a particular coordinate system which they can then understand. So the coordinate system helps to, in a sense, quantify the vector for mathematical usage, okay, for computation. So let's see. So the definition of a coordinate system is easy. It's any mutually orthogonal triad of unit vectors EI, note the hat over there, where I is 1, 2 or 3, defines a Cartesian coordinate system, which we will abbreviate often as a CCS or just a CS. Okay, all right. So there are two types of coordinate systems, a right-handed and a left-handed coordinate system. We are going to use a right-handed coordinate system which satisfies this condition. We are all familiar with this. Now here's something slightly new. So we talk about the notation. So I am going to, so in dynamics it's often common to have many coordinate systems at the same time for the same problem, and it's easy to get confused. So it's a good idea to give them names, and the way our nomenclature is going to run is that we will give a, so if we have a coordinate system, for example, like that, so that's a coordinate system given by 3 mutually orthogonal unit vectors, and usually there is an origin for the coordinate system. Let's call it P. Then the way we are going to give this coordinate system a name, I have this over here. So this coordinate system will be identified as a name. That's the name of the coordinate system, its origin, and the set of unit vectors which form which define the coordinate system. Okay, so that's what it is. Okay, so here we have it. All right. So let me give you some examples of common coordinate systems. This coordinate system we are already familiar with. It's a coordinate system with fixed unit vectors. But there are other coordinate systems which we have used in the past which have unit vectors which change. So one of them, for example, is the cylindrical coordinate system. The way we define a cylindrical coordinate system is that we first fix an axis in space. Let's call that axis EK. Okay, and we measure the distance, and if you want to locate any point in this coordinate system, let's say you want to locate this point P, then we measure the distance of this point P from the fixed axis, and this direction is then defines ER. Okay, the vector EK defines a plane normal to itself. Okay, in that plane, so let me actually draw that plane. So it defines a plane normal to it. Okay, and in that plane I can define a reference line. Okay, and project this point down. Okay, and measure this angle, which let me call it theta. All right, and this defines the third unit vector like that. It is normal to the plane formed by EK and ER. All right, and this triad ER, E theta, EK defines the cylindrical coordinate system, and later on you will find that I will kind of identify them again with E1, E2 and E3. Okay, all right. So that's the cylindrical coordinate system. Let's move on to a spherical coordinate system. Again, we start off with a fixed line in space. We have a point P. We have an origin. Okay, and let's call the origin O, and we have this line over there which then defines this unit vector ER. This fixed line defines EK. Again we have a plane which is defined by as normal to EK. We can project down the point P, okay, and measure its displacement from the reference line. I hope I got that. No, I guess I got it wrong. I'm going to keep it theta over here. No, I got that wrong again. It was phi is fine, so we keep it phi, and we can define this angle as theta. Sometimes people define this angle as theta, it doesn't really matter, and that defines E theta over there, and then normal to E capital R and E theta, I can define this E phi, and then I get this triad of unit vectors ER, E phi, E theta. Okay, and again I can identify this as E1, this as E2, and this as E3, and this identification you will find will be useful when we start computing. Okay, so here are some examples of coordinate systems. Okay. And now I come to the possibly the most important takeaway of today's lecture, which is index notation. So far whatever you have done, whatever I have spoken is kind of familiar to you. Okay, so we start with index notation. Okay, but so the first question you will have is, what is an index? Well, if you remember, we have been using this EI with I equal to 1, 2 or 3. So this creature over here, that's an example of an index. Okay, that's an index. Well, where else have you seen an index? Well, when you are doing matrix algebra, you used to write the components of some matrix as Aij. These are indices. Okay, when you wrote vectors in matrix algebra, you wrote something like this. That is an index. Okay, so these are all examples of indices. Why should we do them? We do them because index notation helps simplify and reduce the amount of algebra we have to do. Also, for example, a very common operation that you will see in mechanics is a triple product, A cross B cross C. And for example, this comes when you are trying to compute centripetal acceleration. Okay, centripetal acceleration will be given by omega cross r. We'll come to it, but it will come to something like this. And this is a very common thing in mechanics. Now, that's a triple product, and this usually gives you 27 terms to compute. That's a lot of algebra. Okay, so what we will find is that the index notation will help simplify the algebra by quite enormously. Okay, but index notation has rules. So let's look at the rules. Okay, so here are some rules. So first of all, let's say equation. We'll typically have equations of this kind: AI bi plus ck dj is equal to ei jk I. Okay. Well, let me not make it too complicated. Ei j d k I. Okay, something like that. Okay, so what this is saying is that an index may appear once or twice in any term in an equation. So here are terms in the equation. Okay, now in this term, okay, that actually this is wrong. I have made a mistake. I'm sorry. Let me correct this mistake. I'm going to erase this and write here a k b j. That's better. Okay, so these are terms, all right, and what it says is that an index can appear once, okay, or twice, but one can never have a term like this: f k k k c k d j. So this is wrong. This is wrong. Okay, these are correct. So these terms are correct, and that's a wrong term. All right. So that's what this statement means. That's one rule. Okay, we have already seen that indices can take the values 1, 2 or 3. For example, when we had EI, I was either 1, 2 or 3. That's in 3D. In 2D, I is only 1 or 2, and really we will not have any occasion to go to 4D. The next important item is a free index. Okay, so what's a free index? So let me again take this example. I'll copy it over here. So this part is the wrong part, so I will only copy this part of the equation. So let's bring it over here and work on that. Okay, so a free index is an index that appears just once in each term. So let's see. So K, it is appearing once in this term, once in this term, and once in this term. So right, so K is a free index. What about J? So J is once in this term, once in this term, and once in this term. So J is also a free index. What else is there? Well, on this side I have I, but that is appearing twice. So I is not a free index. Okay. All right. So we understand what a free index is. Now the second thing it is said over here is the free indices in each term must be the same. What that means is that we have said J and K are the free indices. Every term must have the same set of free indices. So that means I cannot add a term like this. F M G I rather G J K. So why can't I add this term? I can't add this term is that even though J and K are here as they should be, this term has a new free index, right? This term M, in this term M is a free index, but M does not appear here, here or here. Okay, so therefore this now becomes a wrong equation because of this. Okay, let me say M is also a free index, but okay. Alright, so that's what this statement means, that a free index in each term must be the same. Okay, 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 not okay. Alright, okay. As usual, free indices can take the value of 1, 2 and 3. Okay, so now the next thing is a dummy index. So what's a dummy index? Let's again take this example that we are working with. So I will take the right part of this example, bring it over here. Alright, so let's look at this example. We have already said that, we have already said that K and J, let me make it better, that K and J are free indices. Okay, but the other index in this equation, I, and I doesn't appear here, I doesn't appear here, but over here I is coming twice, and that's what is an index that appears twice in each term is a dummy index. So I is a, okay, let me write it better, is a dummy index. Okay, and the name of the dummy index is not important. Okay, What does that mean? That means that if I was to write another equation, let me copy it and put it here. So these two equations are the same, but now I'm going to do something else. I'm going to erase I from here and replace this with m, and these two equations are the same, okay, because the only difference between these two equations is that the dummy index is called I here and the dummy index is called m here, and what we are saying is name of the dummy index is not important, okay. So therefore these two equations are the same. Now one more thing which I have forgotten to put in the slide, but I will put it when I send it to you, is that, and I'll write it over here. Actually, why don't I write it in the slide right itself, okay, and that way we can kind of go over it together, okay. So what we are saying is that dummy index may not be in all terms, okay. So that's what I'm saying. Let's play it again. Alright, so what does this mean? The dummy index may not be in all terms. So over here, the dummy index is over here, but not here and not here, and that is okay. Alright, that's all this is saying. The final thing that we have over here is the summation convention. Now that's very important. So what exactly do I mean? Suppose I have a term like this, AI, BI. What does this mean? So the summation convention says that the dummy indices are summed from 1 to 3, okay. Oh, actually I have written over there, okay, yeah, okay. So the name of the dummy index is, okay, yeah, so the dummy index are summed from 1 to 3. That means, so let's interpret over there that AI, BI is actually A1, B1 plus A2, B2 plus A3, B3. That's what a dummy index does, okay. Now what you also see is that, let me just kind of give you an example of this continuous example. So if I write an equation like this, C is equal to AI, BI, is this equation correct? So let's ask this question, is this equation correct? Well, yes, because that's a dummy index. Dummy index may not appear in all terms, so it doesn't appear over here. There are no dummy indices over there. Are there any free indices? So free indices, no. Well, there is no free index in this term and there is no free index in this term. So this is a correct equation. It's an equation which is correct in index notation, okay, and that's what it is. Okay, let me give you some more examples. Okay, so let's play around with some more examples. How about this equation, AI Bj is equal to Ci? Let's think about it. Is this, is it a correct equation or an incorrect equation? Well, in this term the free index is I and j, but over here the free index is only I. So what happened to j? So this equation is wrong. Okay, let's try one more. AI Bj is equal to Cij dk. Let's think about this. In this term I and j are the free indices. Those are the only free indices. In this term, I and j are over here, but there is a new free index. K is a new free index. Therefore, this equation and k does not appear over here. Therefore, this equation is also wrong. How can I make this equation correct? Well, if I wrote this equation as this is the right equation. Okay. So here are some examples. Let me give you some more examples. Suppose I was to write an equation like this: AI Cij Bk equal to Dj Ek. Is this a correct equation or an incorrect equation? Well, let's first count the number of free indices. Free indices over on this side. Is I a free index? Nope, because it is repeated. So the free indices over here are j and k. And what are the free indices over there? J and k. What about I? Well, I is a dummy index. Dummy. Okay. And as we said, a dummy index need not be there in all terms, and it is not over here. No I. Okay. How about this equation? AI Cij Bk is equal to D. Actually, let me make it even more trivial. Equal to A MC Mj Bk. Well, the only difference between these two equations is that the dummy index I, on this side dummy index is I, on this side dummy index is M, but we know the name of the dummy index is not important, so this equation is also correct. So these two equations were correct. Okay. Any further examples? Yeah, here's the last one. AI dk is equal to Bjj Ek. Okay. Well, that's a dummy index, so it need not come over there, but the free indices on this side are I and k, and on this side the free index is only k. I is not there, therefore this is a wrong equation. Okay. So you can play around. I mean, we'll give you more exercises to do as homework, but that's basically the index notation. And now let's come to what's the point of using index notations. So before we do that, we must kind of understand a few operators which are useful when doing index notation manipulations. The first is the Kronecker delta, which is self-explanatory. Delta ij, which is 1 if I is equal to j, and 0 if I is not equal to j. So for example, delta 1 2 will be 0 and delta 3 3 will be 1. That's an important operation. That's the important use of the Kronecker delta. So over here I have some complicated thing, some nasty object which has many indices. Okay. And at some place I have I and j, and I am multiplying this nasty object by delta ij. Now we know that delta ij is either 1 or 0 depending on I is equal to j or I not equal to j. In this term, I and j are repeated, so therefore they are dummy indices. So we will sum them over. So what would this be? So this p I j delta ij will be p1 1 delta 1 1 plus p 1 2 delta 1 2 plus p delta 2 1, and so on and so forth. So there will be 9 such terms, right? And what you know is that because of this property, this will be 0, that will be 0, right? So you agree that all that will survive at the end of this will be p1 delta 1 1, and then let me just take a shortcut. Oh jeez, paste, paste, and then so this is all that will survive. Oh, but wait a minute, this thing is 1 1 1, right? Center 3. So all that we will have at the end of this is just this. But this, from our previous expertise with dummy indices, is simply, and that is what is written over here. So whenever you multiply an object by the Kronecker delta, it simply contracts the two indices of the delta of the Kronecker delta. Okay, so well, here is an application of this. So well, first an application of the Kronecker delta. So ei dot ej. So if these are orthogonal vectors, what is this? This is simply delta ij. Okay, because e1 dot e1 is 1, but e1 dot e2 is 0. Okay, what about the contraction? Well, here is an example: ai bj ck delta ij. Well, ij, so this must be ai bi ck. Okay, and what is ai bi ck? It is a1 b1 ck plus a2 b2 ck plus a3 b3 ck. Okay, so that's the Kronecker delta and the contraction operation. And one last important object that we will use is the alternating tensor. What's a tensor? We will come to the next lecture, but this is how it is defined: epsilon ijk, which is plus 1 for even permutations of ijk. What are even permutations? So even permutations 1 2 3 2 3 1 3 1 2. Okay, so epsilon 1 2 3 is equal to epsilon 2 3 1 is equal to epsilon 3 1 2, and that is 1. It is minus 1 for odd permutations. What's an odd permutation? These are odd permutations. One 3 2 3 2 1 2 1 3, and what it's saying is that 1 3 2 is equal to epsilon 3 2 1 is equal to epsilon 2 1 3, and that is minus 1. In all other cases, epsilon is 0, so that means epsilon 1 1 2 is 0. Epsilon 3 3 1 is 3 2 1. No, that's not the one I wanted, which is also the same as epsilon 3 3 2 is equal to epsilon 2 1 2, and so on and so forth. Okay, so that's called the alternating tensor, and we'll see how it will be used to make certain operations very simple. Okay, all right, coming towards the end, let's apply the index notation to something. I've almost forgot. We have a very important identity called the delta epsilon identity, which basically talks about if you multiply two alternating tensors, and please note here k is a dummy index, so that's a summation. Inj and ij lm are free indices, and on the right side I is a free index here, I is a free index here, j is a free index here, j is a free index here, and similarly l and m are also free indices here, and k is a dummy index, so need not be repeated over there. And this equation, as you will see, you will use it, it will come in many operations, as you will see. Okay, so now I think we are really ready to go and apply it to some some vector algebra. So here are some vector operations, and which will be benefited by our using index notation. So first thing to do is we have learnt about a coordinate system. Okay, so let's draw two coordinate systems, and I'm going to draw them. Okay, so let's call this coordinate system as with origin P, and let's have another coordinate system, and let me draw it here. Let me use a different color for it. Okay, that's bad, very bad. Okay, let me improve this line a bit. Okay, so here are two coordinate systems. Let this have the origin S. These are given by E1 prime, E2 prime, E3 prime, and this is the name of this coordinate system is script S. This one is P with E1, E2, 3. Okay, and let's say I have a vector, and let's draw this vector. So here is this vector A, and I'm going to copy the same vector over onto this side. I'm going to put it over there. So let me clean up my act over there a little bit. Same vector. This was E2 over this one, E2. Okay, so here we have it. And how would we find the components of this of A? Well, I would drop this perpendicular, I would get this, I would get this, right? That's what I would do. Okay, so on this side, if I wanted the I could write A as AI EI, then I could compute AI as A dot EI. Okay, so these are obvious operations. On this side, I can similarly write A as AI prime EI prime, and with AI prime being A dot EI prime. Okay, and that's what I have, so that's kind of clear. Now what we could do on this side is that we could compile these components in a column vector. So I could compile them like this: A1, A2, A3, and these I would call are the components of A in the P coordinate system. At the same time, I could do the same game over here. I could say the components of A in the S coordinate system are A1 prime, A2 prime, A3 prime. Okay, so now let's kind of talk about this. Here's the green. So the vector is the same. The coordinate systems are different. Okay, so what we have is A is obviously A no matter what the coordinate systems be. Okay, but A in S is not the same as A in P. Okay, so that means, that's what I have said. So in general, AI and AI prime are not the same. Okay, so this is the important conclusion here. The vector remains the same, but components change with choice of the coordinate system. And this is very, very crucial, because you will find that unless you pay attention, with the enormous number of coordinate systems that you may have in a typical rigid body mechanics problem, if you are not careful, you're going to get confused with components. Are they in the fixed coordinate system? Are they in a rotating coordinate system? You will not know unless you diligently follow this notation. Okay, whenever you want to, every such column is identified with the components of some vector but in a particular coordinate system. Always remember to write down the coordinate system's name. Okay, so I mean, I've already given you the example over there, but I can give you a simple two-dimensional example. So here is a coordinate system. Okay, and here is a vector. Okay, let's say this is 45 degrees, pi by 4. So clearly, so A, let's give E1 origin O, E2 coordinate system A. So A is A1 E1. Oh, I forgot to put an E3 here, plus A2 E2 plus A3 E3, and you can compute that A in O will be, and let me give it a length. Let's say the length is root 2, is 110. Now suppose I had another coordinate system, let's give it, which is aligned like this: E1 prime, E2 prime, and E3 prime was the same as this. What would this quantity be? And so this new coordinate system will be O prime. Okay, so what will be A in O? Well, that will be root 2 0 0, and these two are not equal. Okay, so that's the example. Okay, and oh, I made a mistake. This should have been O prime. Okay, all right, last slide. So let's kind of revisit the simple vector operations with index notation. Okay, with index notation. So the dot product A dot B. Well, let's compute. Okay, so what is A dot B? Well, A dot B in some coordinate system, A is AIB, is AIEI. In the same coordinate system, B is BJEJ. Okay, please note that I is a dummy index, J is a dummy index, but in the same term I can't have more than 2 occurrences of the same index. So I can't write something like this. Okay, I can't write this as AIEI. Okay, this is wrong. Okay, because I is occurring 4 times. Right. Okay, so let's get rid of this. This is wrong. Now this is a constant, that's a constant, so let's pull the constants out. So AI bj ei dot ej, what is that? Okay, so that is AI bj delta ij, right? So that is that. And over here now we have a contraction because I, j, j, so this is really AI bi. Okay, and that's what we have over there. Okay, okay, all right, and this equation therefore is also a valid index notation equation because no indices over there, one dummy index over there. And I will leave you to prove that A dot B is also the same as ai prime bi prime in some other coordinate system. Okay, the norm again we can compute simply by replacing b with a. Okay, so that's fine. Let's come to the cross product. Okay, so a cross b, we have already said that this if you have a vector a and you have a vector b, they define this plane and the normal to the plane is given by some vector which we had to kind of compute. Okay, alright, so we had a kind of this geometric picture to deal with every time we thought of a cross b, but now with index notation we can simply have this formula. So let's kind of expand this formula and see if it makes sense. So you all know that a cross b is given by this a1 b2 minus a2 b1 e3 plus a2 b3 minus a3 b2 e1 plus a3 b1 minus a1 b3 e2. Okay, so let's look at this. Okay, 1 2 3, that's a even permutation. 2 3 1, even permutation. 3 1 2, even permutation. Okay, so that means I can, alright, so okay, so that's one. The 2 1 3 odd permutation, 3 2 1 odd permutation, 1 3 2 odd permutation. So it is possible therefore to condense this large equation into simply epsilon ijk ai bj ek. That's what is written over there. Okay, so you can see very well there is no repetition of any, there is no 1 1 2 kind of thing object over there. So you can now compare this and this and convince yourself that this is a succinct way of writing that. I hope you recall this was the alternating tensor. So here are a couple of vector entities that you are familiar with, which we will write down in using index notation. So one is the box product, which says that a cross b dot c is equal to b cross c dot a is equal to c cross a dot b, and this really is the volume of a, sorry, let me draw a better picture. Say if I have a parallelepiped given by a b c, then the volume is a cross b dot c. Okay, I think that is correct. So how do you compute it? We can spend our time doing these kind of manipulations, or we can simply use index notation. So let's do that. So a cross b dot c. Okay, so let's pick a coordinate system. Let's PPEI. So in this coordinate system, let's write down a as ai ei, b as bj ej, and c as ck ek. All right, then a cross b is simply epsilon I j m, using this formula over there, a I B J E M, I have replaced K by M because I have used K over there. So alright, so then I have to dot this creature with C, which is equal to epsilon I J M A I B J E M dot C K E K. Okay, so these are all constants, and these two will be dotted. So this becomes epsilon I J M A I B J C K E M dot E K, and this is delta M K. So this becomes epsilon I J M A I B J C K delta M K. Okay, now wait a minute. M K K. So that's a contraction operation over there. So this means this is only going to be the epsilon I J M A I B J C M. Okay, and well, dummy index its name can be changed. So I am going to change K. So I have changed M to K, M to K. It's a dummy index, so its change doesn't matter, and that's the formula I have. So that's the POS product, and you can make sure that these two also give you the same answer. Coming now to the triple product, here's a familiar formula which I will be asking you to derive using index notation later. Right now what we will do, we will try and express the triple product on the left in terms of index notation on the right. So we begin by choosing by a coordinate system, our favorite one, P, and in this coordinate system we can write B cross C as epsilon I J K B I C J E K, where I have used this formula for B and C. Then I have to express what A cross B cross C would be. So then A is AM EM cross epsilon I J K B I C J E K. Note that I have been clever here. I see that I, J, K have been used twice here, so I can't use them over here, so I have picked some other one, M. Now here is this, and these are all constants, so EM will get crossed with EK like these two. So I will need a formula for that, so which I shall write here, that EM cross EK is equal to epsilon MKL EL. You can check the correctness of this formula. Okay, this you check. So meanwhile this will become epsilon I J K AM BI CJ, and then using this formula over there I will get epsilon MKL EL, which I can rewrite as epsilon I J K epsilon MKL AM BI CJ EL. Okay, so this looks somewhat like this, but of course they are not the same, and that is because all indices over here are dummy indices and we have to rename them to make it look like this. So let's rename them. So here's my renaming. Now look, EL has to become EI, okay, CJ has to become CM, BL, so BI has to become BL, AM has to become AJ. So what has happened? M goes to J, I goes to L, J goes to M, and L goes to I. Okay, so what happens to the epsilon over here? So epsilon, M goes to J, K is as is, and L goes to I, and epsilon ijk, I goes to L, J goes to M, and K remains as is. Okay, still almost there, but there are differences. There is IJK here, is JKI here, it's LMK, LMK is fine, so this is okay, but this is a problem. Well, it's not really a problem, right? So let's get rid of this line to make some space here. We can simply do a permutation here, right? So this, so let's write epsilon LMK here, and this is the same as epsilon IJK, AJ, BL, CN, EI. Okay, and that is what we have over here. So that's it. So that's today's lecture, and I will request your forgiveness for hiccups. This was my first attempt at making a video lecture, and as you will see, online teaching can develop sudden snags, and hopefully we'll iron them out as we move on. Okay, all right.